I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. My name is Taylor Sparks. I'm a professor of material science at the University of Utah, and I'm joined, as always, by my co-host, Andrew Falkowski. And today, we've got two experts from SCHOTT. Now, we have been asked from people to do a glass episode for some time, and it is overdue, like episode 106 or something. How have we not done a dedicated episode on glass? And who better than the pros at SCHOTT to help us out with it? So let's do some quick introductions. Sebastian, how you doing?
I'm doing good, thank you. As a listener of your podcast, I'm really excited to be here. So,
Killer. Sebastian's going to be on the technical end of how SCHOTT is making really awesome glass possible and what are the properties that they're looking for. And we're also joined by Colin. Colin, want to do a quick intro?
Yeah, hi guys. Thanks for having me. I work with Sebastian. I'm more on the commercial side, so I am our regional business development manager for Semicon Glass Solutions, which I know is a bit of a mouthful, but you can picture my role as sort of a technical business development, trying to transition our developed products into an actual customer application.
Perfect. So we've got the person who's making the glass, technical achievements possible, and the person saying, now I've got a business idea for it. This is a perfect team to talk about when we get into glass. So maybe to get started, Andrew, tell us a little bit about glass. Glass is one of the oldest materials. It's something that we as humans have been using for forever. Tell us a bit about it.
Well, the earliest glass wasn't even made by people.
Yeah, made by the Mother Earth, right?
Yeah, that's right. You'll find it in the form of obsidian, which is lava that's cooling and retaining an amorphous structure, or even from meteorite impacts.
Oh, that's
there's something
glassy?
called
I didn't know that.
impactite. Yeah, it's hot enough that it can locally melt the earth around it, and depending on where the meteorite strikes, you'll get different types of
Okay, not
glass.
the meteor itself then. You're saying the area that it hits.
The area that it hits. The impact
cool.
is hot enough, and then if it cools rapidly and under the right conditions, which we'll get into, you can form glass. It really wasn't until about 3600 BC that we start to actually get man-made glass, which is hypothesized to, in many cases, be accidental, just byproducts during metal smelting or ceramic glazing. Things are getting hot enough that sand and other materials next to it can melt, and some of these have glass-forming potential, and that's where that starts to appear. But it wasn't really until about 1500 BC in Egypt that we start really getting controlled manipulation of amorphous solids in the formation of glass and the ability to then dye it into different colors. There's a number of different pharaohs who are buried with man-made glass.
So when I was on sabbatical, we had a chance to pop over to Venice, right? Venice is famous for glass making still today, and historically has been. There's like 1,000-year-old sort of legacy they've had in glass making. And one of the cool things that they were able to achieve colored glass, right? And this was all artisan, not necessarily knowing the science behind it, but figuring out how to get colored glass, colorless glass for crystal. This has been sort of a trade material that for a long time people have been looking at.
Yeah, they were really famous actually for the clarity of their glass and the extent to which it lacked color, actually, because that's all about removing impurities and achieving something that looks just like crystal and glass was very hard to do until on the Murano Island, they were able to concentrate enough scientific understanding and development to enable that production. And this led to other things like the ability to create lenses for the first time, which revolutionized not only our scientific understanding, but our understanding of our place in the universe even. That's what enabled a variety of scientists to be able to look out beyond just our mere Earth.
that was actually also kind of the founding story of SCHOTT as a company, because there was this scientist that wanted to have really good lenses, and he needed a glass maker to make the glass for him. And this is actually how SCHOTT was founded, as kind of a collaboration of like someone who was working with microscopes and optics and a glass maker and the physicist who did all the calculation for that.
That is so rad. The ability to make lenses, right? You have to shape these things. These are actually intentionally shaped. But on the other end, getting it completely flat was a pretty big deal too. Having an unshaped piece of glass, right? So the 1950s, jumping way ahead, right? This was a pretty revolutionary time. We have the Pilkington brothers in England. They came up with the float glass process, right? Basically by floating it on some molten metal surface or you can end up with a very, very flat, distortion-free glass.
That's to me one of the most unbelievable parts of glass making is the industrialization. I mean, you described it accurately. Float glass processing today depends on basically extruding a vat of molten lava, so to speak, across a bed of molten tin, and do the density differences, the glass floats on top. So when you walk next to this gigantic tank, on one side you have this red hot batch of what's essentially a silicate-based lava or other based lava, and then you walk right next to a bed of molten metal, and on the other side comes out these perfectly flat sheets of glass at a scale that's almost hard to imagine.
Do you think that was intentional, or do you think that was just like, I wonder what will happen if we try this? Like, who thought to put? Yeah, that's pretty wild scenario.
Yeah, it's a wild idea. Yeah, that's true. But I mean, it's still what's done today for probably all the windows we have. We're floating on a tin bath. And then on the other hand, you can also make it super thin there. You can make like 400, 500 micron thick glass also on this tin bath. And yeah, as Colin said, it's like a very cool mixture of like lava and molten metal.
Definitely very creative. And continuing with just some of our broad strokes history, there's a couple of really interesting glass creations and maybe even misnomers that have popped up. You have the Lycurgus cup, for example, which is this 4th century Roman glass vessel. It's worth looking up. And it was one of the first instances of nanomaterials being accidentally introduced. In this case, it's gold and silver nano materials, and it produces this what's referred to as a dichroic effect, where if you're just looking at it under light, natural ambient light, it has this pale kind of greenish look. But if you shine a light through it, it changes to a red. And it all has to do with some really unique physics that are going on that were seemingly accidentally discovered, but are preserved in this this cup. It's worth looking up. Another misnomer.
It probably took us like 2,000 years to understand how it works, from them making these gold nanoparticles to us finally figuring out what's actually happening in this glass.
So cool.
Yeah, it did require quite a lot of sophisticated analytical methods. Certainly not till relatively recently that we're able to actually understand it and even mimic this effect. Another common misnomer is if you ever go to the cathedrals throughout Europe or even in the US, you'll see that the windows, the stained glass, tends to be thicker at the bottom. And for a while, people thought, oh, this must be the glass, which is kind of like a solidified liquid slowly trickling down. But that's not the case.
I actually made this a homework question because I was like, this is so absurd. I have to like have them do the math on how long it would take to flow. Spoiler alert, it's not that.
This is like the number one myth about glass. I think that it's just like viscous, but it's just super viscous, but it's still kind of a liquid. But here's your first glass fact. It is not. It is solid. And the people were just smart that they were not good at making flat glass or evenly flat glass, or they were just putting the more stable, thicker part at the bottom of their windows. But it's not the glass flowing down over the centuries.
Yeah, it's not a different version of the pitch drop viscosity test or anything. It's truly just a byproduct of manufacturing. Although you can understand very clearly how, learning that glass is an amorphous material like a liquid, you can see how that conclusion would be drawn. But yeah, that's been proven quite unsubstantiated. So.
Well, for our listeners, we try and be pedagogical in this podcast. We'd like to teach some things, and I imagine some of our listeners may not be super familiar with the fundamentals of glass. So let's go through some of that. Glass is a disordered material, right? It's not like the crystalline materials, which we've done many episodes on, where things have a nice crystalline structure, every atom in its place. Glass is sort of the exact opposite of that. You have a hodgepodge, you have a jumble of atoms. A good mental picture is to think of a liquid and then take a snapshot of time and freeze it, and that is your glass, right? That's actually, I think, a pretty good mental model for this. Now, the big question is, how do you achieve that? We know that things, energetically speaking, like to organize themselves into crystalline structures. There's usually a net stabilization in terms of, a formation, enthalpy, for example, right? So why wouldn't it do that?
I mean, if you look at it from the thermodynamics, it will crystallize. It's just the kinetics that prevent it. And you can imagine that if you have your glass melt and you cool it down, that it gets so viscous and all the movement gets so slow, and that it kind of freezes in before it can actually crystallize. That's basically the trick. You have to freeze it in or cool it fast and it can crystallize. And some people may say, yeah, it's like freezing, like first order phase transition of thermodynamics. It is not. Glass transition is a bit more complicated than that. But for the sake of it, I think we can go with freezing in a liquid before it can crystallize.
That's perfect.
So then to do that, we want a relatively high viscosity around its melting point, preventing the rotation or rearrangement of these atoms into a crystalline form. It sounds like we also want a sufficient crystal complexity.
Yeah,
right?
you want degrees of freedom. Like the basic building block of most glass, plenty of exceptions, right? But silicates, right? Silicates forms this SiO4 tetrahedra, right? So you've got this silicon surrounded by 4 oxygens, and that's going to link up to then 4 other whatevers, usually other silicate groups. And each one of those can rotate. So you've got a lot of flexibility. And then you add modifiers, right? Things like sodium or calcium that are going to disrupt this lattice. All this additional complexity, again, it could crystallize and it can crystallize, but it takes time. And it allows you to cool these things down at a more reasonable time frame without getting crystallinity.
Yeah, I think it's like if you think about like your atoms in the melt and how they're moving, if you think of them as like little billiard balls, that would be like no glass formers. That's like you melting like sodium chloride or so. They can arrange relatively easily, and so it's very hard to make like amorphous sodium chloride. But if you have like your silica, they have these tetrahedra, and that's some kind of constraint that it will be in this tetrahedral conformation, and they have certain like angles and bond lengths that don't really change even in the glass. And this constraint that makes all the movements much slower. And this is why silicate is such a nice glass former.
Something that I was learning about in this episode as we were putting these notes together that I don't think I'd realized before is that if you cool things down really slowly, you're essentially giving it more opportunities to pack more tightly together, more densely. So the density of the glass is then going to be related to the cooling rate. So this is a design parameter, which I don't think I'd appreciated before, because the density of the glass is going to be related to all sorts of things. In fact, we're going to do a segment on in today's episode on the refractive index. And now you've got a tool for tuning the refractive index. I think that's really cool.
Yeah, that's true. And I mean, that's actually what's used in the industry, especially with optical glasses. It's like really about fine tuning the refractive index. You do it up to like the 5th digit behind the comma. And you do that, I would say the coarse you do by the composition, but really the fine tuning in the end, you do that by heating and cooling the glass with a very specific temperature profile. And this is how you can really narrow it down to like 5th, 6th digit behind the comma.
Dude, that's so rad.
Another thing I hadn't really appreciated is that silicon oxide is a common network former, but there are other ones too, including boron oxide, phosphorus oxide, germanium oxide, low coordination environment atoms.
Yeah, you can have different building blocks, not just the SiO4 sort of building block. You can have other ones.
Yeah, and it's very common actually to have in most classes to have combinations of them, especially the combination of like silicon with boron and also a bit of alumina that works really well. So most classes today are just like have like we always think of them as like different oxides put together, and like in like commercial classes you have 5, 10, 15 different oxides in it. So this is why we always laugh if people talk about high entropy alloys or high entropy oxides. It's like, we're making high entropy oxides for decades.
Yeah, absolutely.
And from a practical perspective, one of the things that interests me is the incorporation of these, various network formers or modifiers is technically required in order to batch melt these glasses at really large volumes. The temperatures required to melt a pure silicate glass, something like a high purity fused silica, which is an amorphous. We can get into the technical semantics between quartz and quartz glass and why that can be confusing. But the incorporation of these network modifiers enables us to actually melt glass at a temperature that's sustainable for extraordinarily high throughput.
Absolutely. So it's a very practical thing as well. All right, we have a lot more to say about glass, but given the time, let's keep moving some big picture stuff. When we think about the properties of glass, what properties come to mind? Material scientists, right? We know, you've dropped a plate before you've dropped a glass. They are brittle. They are hard. They tend to be high melting point. They have this amazing possibility of, in many cases, being transparent. Try that with a piece of metal, right? It's pretty remarkable. These are some of the reasons. Those are standout properties that have enabled them to have really cool applications over the years, right? They're scratch resistant. You can see through them. Obviously makes great for windows and screens. You have this ability to have a structural building that you can actually let exterior light into. No wonder people jumped on these as early as they could.
Yeah, and I think one aspect that also makes it really interesting is like their flexibility compositional wise, because you're not restricted to a crystal stoichiometry. You can really just have like basically like a seamless adjustment of your composition. And also that obviously allows you to really fine-tune your properties. And I mean, I'm a chemist by training, and if I think about which oxides I work with, it's basically the whole periodic table.
Yeah.
You can basically put anything in glass. There's just like a handful of things that don't really go into a glass, but the majority of the periodic table, in the form of oxides especially, you will find in some glasses.
They also tend to be electrically insulating, although they don't have to be, which can have a number of nice properties in the semiconductor industry, which we'll get into. And they can be, because of this amorphous structure, they tend to have very sluggish diffusion through them, which is used in a number of waste containment applications.
Right.
I think if we're talking waste containment, we're talking about radioactive waste. Like one of the main ways of containing it is just like melting that radioactive waste into a glass. So they're like actually very specific glasses that are very stable, very resistant to corrosion and also radiation, because you want this to be in this glass block for like thousands of years.
Yeah, another good example would be the sort of pharmaceutical packaging industry, which comprises a significant amount of our sales. When you're looking at extraordinarily low diffusivity, you're able to package materials that are very sensitive to leaching. So you're looking to avoid any contamination of a packaged product. Glass is a extraordinarily stable material in which you can package those products.
And then one of the properties specific to SCHOTT's expertise has got to be the refractive index. So we've said previously that glass is this amazing material because it lets light through it, but it doesn't just let light through it. There's some nuance here, right? As light enters the glass, because of the difference in the refractive index between air and the medium that it's passing through, glass in this case, because there's a difference, there's a bending in the light, right? And this bending we can actually use to manipulate all sorts of things to get lenses by designing the optical path that this light is going to pass through the material. We also end up with this concept of dispersion, where the bending is not the same for all wavelengths of light. It's going to be different for different wavelengths of light. This is going to be important for, if you're familiar with transmission electron microscopy, we've done some episodes on this, for chromatic aberration, basically using this differential light bending to our advantage to, in this case, focus microscopes.
Yeah, I think if you think about the optical properties, I think this is like one of the main motivation to use glass. And if we look at our glass portfolio at SCHOTT, I would say probably 70% of our glasses are optical glasses, even though they may be made just like 10-20% of the revenue. So there's a very famous diagram. It's the so-called Abbe diagram, also named after one of our founding fathers, Ernst Abbe. You should look that up. It has like a lot of optical glasses, and on the x-axis you have like the refractive index, and then you have the Abbe number, or the dispersion, on the other axis. And this is kind of a map of all the glasses with their specific optical location, and you really need these to build your optical devices, and optical designers need all this variety of different glasses, and this is why they exist. This is why we make them.
Yeah, for student or industry listeners out there, it's a fascinating experience to go to something like the SPI Photonics West conference or the Optics and Photonics conference. You have the conference side of things to understand the technical background, but it was mind-blowing the first few times I attended. You see the industry trade show where you have companies like SCHOTT and people that use our materials that have, 80 to 100 different lenses on a countertop, and their product data sheets show these refractive indices out to, as Sebastian mentioned, 5 or 6 significant figures, with exceedingly minor differences between them. But every single one of those fabricated lenses serves a specific industrial application, and that precision is required for the function of their kind of end devices. So it's fairly mind blowing how complex it gets.
And on that note, how do you actually achieve that fine tuning? Is it just through processing? I think you mentioned also composition. What sort of parameter knobs are you tuning to achieve these subtle differences?
So like the processing, this is really just the fine tuning. I would say if you think about what range do we have with the refractive index, so we start around like, let's say 1.5-ish. This is roughly what most silica-based glasses have, but it goes up all the way to 2 and even beyond 2. And you do that by the composition. So to go to these like really high refractive indices, and everything around 2 is really high, you need you don't achieve that with your classical glass formers anymore. So like your silicon oxide or your boron or your phosphorus, they give you all this 1.5-ish refractive index. So you need to go down in the periodic table and look at lanthanum or barium, titanium, niobium. People used to use lead, even like radioactive materials like uranium and thorium, and use that anymore for obvious reasons. But you're working with like really interesting elements, and especially like these very heavy elements, and that makes the glasses also very challenging to use, because you don't have these nice glass formers anymore that give you your viscosity, and so these glasses are super prone to crystallization, and that's actually one of the main projects that I work on. So I'm really passionate about it.
Hey, Sebastian, so I remember learning about refractive index, but it's been a long time. Help me understand. I thought it had to do with the density, right? Because the light travels different speeds as a function of the density of the medium it travels through. And so if you go to higher densities, because you're saying going down the periodic table, going to lanthanum, all these crazy things, right? Mm-hmm. Is that really just the elements you're choosing are really just a pretext to increase the density, essentially?
Basically, that's what it is. So it's like there are actually like two mechanisms, but I would say it's mostly like density and also like the polarizability of your metal cation, or even like the oxygen framework. Maybe I studied. So it's like the polarizability of your glass itself. It's these two. It's like electronic density and polarizability, but you will find both if you go more like towards the heavier elements.
Have people done anything really crazy and messed with the oxygen side? Sulfide, selenide, whatever else? Or do you not get transparency over there?
No, you actually can make very interesting materials there. You can make oxynitrides. They're very fascinating glasses, because like the nitride, because it's like it forms an even stronger linkage in your network. So they're very hard materials, but they're super hard to manufacture because the nitrogen wants to go out of your melt. So you can't melt like in a tank under atmospheric condition. Our colleagues in the US, they work a lot with chalcogenide glasses, so based on sulfur or selenium, or so as the glass former. These are not transparent anymore in the visible, but they are transparent in the IR.
So okay. So there are applications for that, I'm sure.
Yeah, very, very different applications, but still glass.
Still optical end-use applications, just in a different sense. Instead of visible light, we're dealing with IR optics for, temperature sensing or night vision, things of that nature. So,
radomes, probably.
Exactly. You can imagine there's a lot of defense-related applications. Yep. So it's optical, just in a different wavelength spectrum.
Okay, so composition is a cool parameter for tuning refractive index. I imagine that defects, for example, from the container where this is happening, must be a big deal, right? You have to put this glass in something, and what if the container in which it's interacting either serves as a nucleation site, giving you crystallization when you don't want it, or defects coming into it? What's this concept of containerless melting?
Maybe just one word on the container, because I think that's interesting for the audience. Yeah. The standard container material we use in glass industry is platinum. So you have all these like platinum tools and crucibles in your lab, and you have to be very careful.
Make sure none of those walk off.
Exactly.
I bought one of those. As a faculty, I bought one. I was like, don't lose this thing. It's lost. I don't know where it went. Dang. It was like a couple grand for a tiny crucible. It's gone.
Yeah, and we have big crucibles. We have like big parts in tanks.
Oh, jeez, I can't imagine.
I have no idea how much worth in platinum that is, but it's a lot. So yeah, that's about like the classical container, and I think the containerless melting is a technique that came up in the last years, where you basically have a small drop of glass and you have it levitate.
How are you levitating it?
Waves. I think you do it like acoustically.
Oh, okay.
And then you heat it with lasers, and then you turn the laser off, and then it cools immediately.
Gotcha.
And this is when we're talking about that you want to freeze in your glass, you have extremely high cooling rates in this case, and this is how you can make a lot of compositions into glass where you would not be able to. We call it vitrify. To make something into a glass that you would not be able to vitrify if you just cast them like we would normally do. I would say it's more an academic concept to
It
really
sounds like it.
expand like
Yeah,
like
can you do this at scale? Like, could you make
I
a ton of glass with this method? I don't think you could.
I know another maybe with that particular method I could see scalability issues, but there's a kind of vertical plasma based continuous melting for some sort of active oxides. I know the battery industry is looking at this, where you can picture just a large vertical cylinder based chamber, and you're exposing sand that you inject at the top falling through the chamber under extremely high temperature plasma that serves as a continuous melting process. The problem being you can't form monolithic structures from that. It's used to create fine powders, glassy powders of kind of metal oxide based glasses.
That's
But
way
from
cool.
the acoustic handling, maybe there's a sci-fi world where that scales, and we'll be approaching that at some point. But Sebastian, I can't see that fitting into one of our plants today.
No, we actually had quite some discussions there because people found papers when we were looking into these high refractive materials, and they're like, these people made lanthanum niobate into a glass, and it's like, yeah, it's like
Milligram
it's like
scale.
it's a milligram. It's like a 1 millimeter bead. Like you asking me for like a 300 millimeter wafer. That's something very different. We won't get the same cooling rate. So this is why it's like it's still very interesting for us because it gives us some guidance where to look, where you would find like glass forming compositions, but it's not a manufacturing method as of today.
Okay, so containerless glass is helping us prevent impurities coming from the container itself. But that doesn't mean that all glass is void of intentional additions. And in fact, maybe the terminology needs to switch. Here we're calling them dopants. We're intentionally adding other species with a very specific job to do. And correct me if I'm wrong, but I think lasers are a good example of this, right?
Yeah, exactly. So you can use the glass as a host material for some rare earths that you use that have like very good lasing properties. And I don't know if you heard about it. I think it was like late 2022 when they had this breakthrough at the National Ignition Facility
Oh
when they
yeah, where they
first
hit it
time
with
had like
200 lasers or something.
yes, exactly. And these lasers, they were operating with shot glass. I don't know, maybe
Oh,
Colin
that's so
can touch on
cool.
that a bit more, but it's such an amazing thing.
Yes, so basically, this is a neodymium doped laser glass, and the National Ignition Facility, part of the Lawrence Livermore National Lab, has kind of their fusion test bed, right? And that fusion test bed, you can picture this laser. It's not a laser pointer that you might hold to point at a presentation screen. Instead, it's an entire building, and that building has over 4,000 pieces of basically meter square laser glass. These are large pink chunks of glass that we melted within SCHOTT, and those are held into frames and pumped with a laser pump. Over 40,000 optical components then kind of guide the light through the self-fabricated laser, which directs itself at a tiny, basically pea-sized tritium deuterium-based, fusion fuel to create the first, actually up to 3 now, net positive gain fusion experiments. So that's kind of a massive breakthrough for the world, and very interesting from a laser glass perspective.
Huge for SCHOTT. I didn't realize that you guys were the laser manufacturer, the glass manufacturers for that. That's so cool.
Yeah, we're extremely proud of our participation there. It's something that we've supported in the past, and obviously it's an ongoing experiment now. You have challenges associated with scaling the NIF form factor, but
Sure.
continuing their experiments is like critical for building a foundation for scalable fusion in the future.
Very cool. Maybe to transition away from some of the optical properties, I have an electric stove at home with a glass top. And from what I know, just handling glass, if you heat it up or you cool it down too quickly, it can shatter. But something's going on here with these glass stovetops. Maybe we can talk a little bit about how you can tune thermal expansion of glass in order to make something like that possible to avoid it shattering.
I would bet that it's actually not just glass that you have, that it's a glass ceramic. And I think this is like one of the biggest advancements in glass science that we had in the last 100 years. It was more or less discovered by accident. I mean, like we were talking about that glasses, they want to crystallize thermodynamically. And there's this very cool glass of materials where you fabricate a glass and then you crystallize it in a controlled way. And if you do it right, you're able to just create like a lot of little nanocrystals into your glassy matrix, and that's what we call a glass ceramic. And I think what people have on their cooktops, especially like these black cooktops, this is a glass ceramic, and the interesting thing is the crystals there, they have a specific property that they shrink when they heat it up. Usually, most other materials they expand because, like, if you increase temperature, the bonds get longer, and also this is the same for normal glasses. Like the thermal expansion coefficient is positive. But these little crystals, they have a negative thermal expansion. If you just balance this right, then you can get like a material with more or less zero thermal expansion, and it's perfect to cook on because you have like your hot burner under it, and you put the cold pot on it, and you don't get
No thermal
stresses because you
stresses.
don't have like thermal expansion. Yep.
So, Sebastian, help me understand these glass ceramics a little bit more. Are these achieved just by your cooling rate, that you're allowing it to cool and begin to crystallize, but you just interrupt the crystallization? You don't let it fully crystallize? Or how do they actually do this?
The standard way of doing this is actually that you make the glass and have it cool completely. We call it a green glass. And then you have this room temperature glass, and then you put it again in an oven, and you heat it up to a temperature where it can crystallize. That's like the most simple way of thinking about it. Actually, the process is a bit more complex because if you do it just like that, you get kind of like all size of crystals in it, and it might not be transparent afterwards because the crystals grow too big and all that. So what you do is you having like an additional step that's called nucleation. So put an oxide in your glass that has a low solubility. It's usually something like zirconium oxide or so. And what happens is if you heat your glass, not to the point where it crystallizes, but slightly below, this zirconium might or will precipitate. And then you have all these nanocrystals of zirconium oxide, and then you just have then you go up with the temperature, and then your matrix glass will crystallize, and it will crystallize on all these small nucleation sites, and this gives you a very uniform distribution of small homogeneous nanoparticles. And that's like I would say the main way to make a good glass ceramic. So you need nucleation and then crystallization to get like the maximum control over your process.
That makes sense. And this probably has applications beyond just cooktops, right?
Yeah, it's a wide-ranging material. So Zero Dur is sort of our name brand, kind of biggest mover from a glass ceramic perspective. I always like to use the example of, you may have heard the European South Observatory has the extremely large telescope, very novel naming convention. So this is a telescope that's in construction in the Atacama Desert in Chile. It's being built at high elevation in a desert to basically have zero light pollution. And it's comprised of we've produced at least 949 of these gigantic Zero-Dur blanks, which are then machined into hexagons. And those are assembled then honeycomb style into an extremely large reflecting mirror. So they get coated with an optically reflective mirror type coating. And the reason that they have to use these basically zero CTE or low expansion glasses is when you're collecting light that will see hundreds of thousands of light years into the future, the dimensional stability of the primary reflecting mirror and the collection mirror directly determine the resolution of the image that you can produce. And so having this basically near, fully stable material enables the collection of that light in a very controlled way.
You do yourself a favor and Google Zero Dur ELT. That is some science fiction stuff. That is an incredible project they've got. That is so cool.
It's pretty wild. Yeah, we're quite proud of that one as well. And these types of materials are utilized in a lot of other, we'll call it satellite-based telescopes, optical components utilized in outer space environments where you have these extremely low temperatures that swing quite a lot when they're exposed to direct solar radiation.
Yeah.
So it enables these extraterrestrial optical investigations, so to speak.
Dude, that's rad. Now, maybe one last thing to touch on before we leave the thermal expansion topic is, Colin, you said that one of the primary things you work on is semiconductor packaging, right? These are also finding use there as well?
Yeah, correct. So CTE in glass isn't just a function of utilizing glass ceramics. So we can tune the CTE of purely amorphous glass as well. There's an emerging world that some of you may be aware of just based on public press, looking at creating, we'll call it larger and more stable semiconductor packages in order to basically build these extremely large surface area computer chips, packaged GPUs that enable the high performance computing for AI applications. So the foundation models require, hundreds of thousands of these GPUs. As they're scaling, the materials that they use today, which is largely polymer based, aren't able to achieve the kind of overall performance required. So glass is incorporated into that substrate. The primary metric that determines success of those packages utilizing glass would be matching the coefficient of thermal expansion to the materials that are used to coat it and build up a substrate, basically. So it's the ability to adjust the CTE, at least in the silicate glasses that we're interested in, somewhere between 2 and 10, enables these package designers to get pretty creative, and enables glass to replace some of the more conventional products used to package the devices that are powering ChatGPT. So it's pretty interesting space.
Right.
Yeah, that makes a lot of sense. Those things get hot. And you also have a really complicated thermal environment too, because at the same time they're getting hot, they're also trying to cool them. And so that makes a lot of sense.
Yeah, the kind of local heat flux as it moves through a package and its interaction with the underlying glass is what drives, the ultimate reason why CTE is important is for long-term reliability. You have a layered system with brittle silicon chips on top, and that needs to stay flat over time to prevent the solder bonds from breaking open, let's say. And so carefully tuning the CTE for managing heat flux through that system enables you to have a flat package over time, which may sound simple, but is the kind of single largest engineering challenge in building these advanced semiconductor packages.
Well, there's one last key material property that we're going to cover today. There's so much more we could cover, but let's talk about mechanical properties because, again, going back to your average person's interaction with glass, it's pretty amazing, but its Achilles heel has got to be its ductility. This stuff breaks really easily. So fortunately, we've made some serious strides to improve the mechanical properties of glass over the years, and now it can do some really great stuff. Yes, it is a high-strength material. Yes, it's brittle, but we can now engineer it to have some really interesting characteristics mechanically, including things that start to look a little bit like toughness. You want to dive into that with us?
Yeah, for sure. This is as you mentioned, an extremely important topic. People know glass as being this brittle material. Their personal experiences, handling glass on a day-to-day basis don't necessarily align with the kind of more industrial applications of glass and the methods and materials that we're using in order to make it a more strong material, so to speak.
I think the strength of glass, you need to be aware that that's a surface property. If you just look at the theoretical strength of glass, it's super high. It's like several thousand megapascal. But if you then look at the practical strength, it just really goes down. Like I think it's like 2 orders of magnitude lower than the theoretical limit, and that's because glass always will have some surface flaws. It's just like microscopic cracks you don't even see, but this really decreases your glass strength when it's used. And so this is I think what makes it brittle. And for example, like I think the best surface quality you can get is a glass fiber. And then I don't know if you handled a glass fiber before, you can just bend it, and it's like they're really amazing, and they give you this really impression that it's very, very stable, and that has a lot to do with the good surface quality of a glass fiber when you draw it, because you don't have any contact, so it's kind of like the containerless melting in a way that we touched on.
Something I remember learning about when I was a student is this idea that a lot of the glasses that we use, they're not like the same properties through the bulk. In fact, the component has been engineered to have different properties on the surface versus in the center, right? And if maybe you've heard the terms tempered glass or ion exchange, right? These are trying to take advantage of that principle where essentially what you're trying to do is, like Sebastian just said, your fracture is initiating from the surfaces, right? So what if, again, if the crack requires tension for the crack to split a little bit further open, what if you put the surface under compression, right? And in doing so, that means you're going to put the bulk under tension inside the glass. But therefore, in order for that crack to elongate, you would first have to overcome the compressive state that you've put it in, right? Now, the downside of that is that when it does break, now you've got tension on the inside and it freaking shatters. But if you've looked at vehicles glass, like if you've ever noticed like a car crash or if you've accidentally busted a window on a car, when it goes, but it's surprisingly strong because these have been, through different mechanisms, either thermally or chemically, we've put the surface under compression. which then creates the center under tension.
Yeah, you're absolutely spot on there. And it's as you said, it's like you have both methods to strengthen your glass to put the surface under compressive stress thermally and chemically. I think what the classical way is thermally. This is what you just described. But you do it especially when you have. Or let me start like that. You do thermal strengthener of glass in a way that you heat it and then you kind of cool it off quickly. You kind of blow on the surface so that the surface cools quicker than the inside. So that means the surface will freeze in while the inside is still molten or viscous. And it will still, as it cools down, the surface is frozen in while the inside still contracts. And this gives you then this compressive stress on the surface and the tensile stress in the middle. But to do that, you need to have, I would say, some glass thickness to get like a reasonable stress profile that you can work with. So this is why you use it for like thicker glass, like I don't know, like centimeter, 2 to 3 centimeter glasses. The main application actually for tempered glass that I feel everyone or I don't know if everyone knows it, but everyone uses it, is your smartphones. All the covers on your smartphones and smartwatches and also laptops and iPads and whatsoever, this is all chemically strengthened glass, because if it would be normal window glass, your phones would just shatter all the time. You would just sit on them and they would shatter. And so there you do a different process. You do something that we call chemical strengthening.
Yeah, tell us how this works.
So right at the start, we thought we talked about that glass has like silicon oxide as the network form, and then it has these so-called network modifiers.
Sodium, calcium,
like
right?
Sodium oxide, exactly. And what you can do, let's take sodium. So we have this glass, it's like this nice silicon network, and then we have sodium in there. We take this glass and we put it into a bath of molten potassium nitrate, 400 degrees C melt of potassium nitrate. It's very aggressive. It's not nice to work with, but people do it in the industry. And what's going to happen is that the sodium will migrate into your salt bath while the potassium migrates into the glass. Because at this 400 degrees C, your alkali ions are very mobile in the glass. They can move. They're not fixed. It's just your network that's frozen in, not the alkalis. And so once you have that, you will get sodium in your salt bath. You don't care about that, but you have the potassium in your glass matrix, and it sits, the big bulky potassium ion sits on the small sodium side, and that will create your compressive stress. And that's what's done with all the cover glass. It's actually more complicated than that. You exchange potassium and sodium because you have also lithium in your glass, and you create these like complicated stress profiles to get like maximum strength of your glass.
Yeah, so and this extends beyond your traditional cover glasses that you may be familiar with. Where the industry is moving with this technology is creating extremely high compression on very thin pieces of glass. If any of you have handled glass that's below, say, 100 microns at thickness, it starts to behave more like a piece of paper than a traditional piece of glass that you may be familiar with. By driving that thickness even lower, we can create what we call a bendable glass, right? Something even with a bend radius as small as less than 1 millimeter. And when you have an extremely small bend radius and an extremely strong glass from a surface compression perspective, you can imagine usages in applications such as the foldable phones that you may see on the market today. So that's enabled by this chemical strengthening process, and then also fabrication of extremely homogeneous thin sheets of glass.
This has been fascinating, guys. But it's clear to me why SCHOTT has the market capture they have. You guys are really good at this. You're innovating glass into not just one direction, strength or optics or whatever, in multiple directions, which is really cool. But I'm curious, what does the future look like for you guys?
I think there's this one big challenge for the glass industry is glass industry traditionally relied a lot on fossil fuels. Like you have your big tanks and you need to fire them somehow. You need to these high temperatures, and we want to be carbon neutral. And so there's a lot of research going on into like process development, how to heat your glass not with gas and oil, but to do with electricity and microwaves and hydrogen and plasma. So there's like really cool process development going on there. I think this is one of the big challenges or directions that the glass industry is going. And I think the other one is, I think you've seen it throughout the episode, like glass enables a lot of very cutting edge technologies. And we as a glass company and as the scientists and developers there, we need to get some basic understanding how these things work to make the best glass for that. And that's very interesting about our job, but it's also very challenging if you have to have an idea about like telescopes and semiconductor industry and like batteries and all that stuff.
Yeah, I see, these ongoing challenges. People think glass is solved to a certain extent sometimes because it is, when you look at the compositional space, Sebastian mentioned it's exceedingly vast in the sense that you can incorporate, most of the elements on the periodic table into a glass.
Any ratio, that's like the thing. You have basically, there's like an endless number of different glasses.
And what we're finding, or the day-to-day challenge, as Sebastian mentioned, is we have these emerging applications, things that we couldn't have envisioned before. We didn't know a cell phone would exist in the 90s, and now we're dealing with one that you can fold up and put in your pocket with a piece of cover glass on it. So the chemical strengthening process had to evolve as a function of that, and that relates to the kind of underlying glass material, as Sebastian mentioned, in terms of the network modifiers that you incorporate to optimize ion diffusion. But even beyond that, we have emerging applications in the medical space, in astronomy, in any of these end-use applications that are going to require smart material scientists to develop the fundamental glass and then also work it into a usable device. So I would say beyond the big challenges, as Sebastian mentioned, it's just getting enough expertise into an organization like SCHOTT to be able to quickly address some of these emerging challenges.
And maybe one last comment, like if you're talking about where something is heading, then you cannot forget to mention AI. And it's the same for the glass industry. Obviously, there's a lot of you had a lot of nice episodes with people from Microsoft, like how much AI is changing material science. And the same is true for glass. I mean, we are also having a team at SCHOTT, our computational materials engineering team, that deals with predicting glass properties from their compositions with machine learning models, and also like reverse engineering and all this. Like you want certain properties, and then you ask the models like, what kind of glass do I need for that? And I think this is also one of the big challenges, but also opportunities that we have in glass science or material science in general.
And it's such a great playground because of how flexible it is from both a composition standpoint and a processing standpoint. What's kind of interesting is, despite it having so many applications and having such cool material science, there often aren't really classes for glass in many material science departments.
It's like an afterthought, which
unless
is
you have
really
a professor who does that specifically. And so I was wondering, where could students or engineers who want to learn more go? Are there any great resources or conferences?
I mean, I think glass, as you said, it's really a niche topic. And I feel even most of the people we have at SCHOTT kind of learned it on the job. I mean, I was like I worked on biominerals, so I had nothing to do with glass before I learned about it. So you might be lucky to be at a university that has a faculty for glass. I don't know, for example, Penn State in the US is very known. But if you're interested in this, involve them. And there are like other resources you can use. For example, the International Committee on Glass. They offer workshops. They have a nice summer school. I think there are tape or journals specifically focused on glass.
And despite their contradictory name, ACERS, the American Ceramic Society, does quite a lot with glass. Beyond Penn State, you have curriculum at Alfred, MIT, Georgia Tech, et cetera, that are all either experienced in glass or building up kind of glass-specific programs. So in the U.S., there's resources that are available and emerging. But as Sebastian said, most of us learned on the job, and kind of having that fundamental material science with a skew towards inorganic really helps build a good foundation for that.
Well, Sebastian, Colin, this was fantastic. A glass episode was long overdue. Thank you to the good folks at SCHOTT for bringing in the expertise for us to do this topic justice. I'm sure we will have more to say on glass in the future. Thanks for joining us.
Thanks for having us.
No, we really appreciate it.
Okay. Huge thanks to our sponsors for this show. Obviously, this episode was sponsored by SCHOTT. You've just heard us talking about just 3 examples of critical properties and then technologies that arose from them. SCHOTT is number 1 in the game. They're doing phenomenal stuff over there. But we're also sponsored by the American Ceramic Society. Now, you heard at the very end of this episode, us talking about resources. We want to point out that they have some great resources for you to dig into to learn more about glasses.
Yeah, that's right. In fact, the May 2025 issue of the Bulletin, which you will have full access to if you use our link, was all about how to improve sustainability and functionality in the glass industry. If you're interested in learning more about glass and you want to know about its future, it's right here.
Perfect topic.
But beyond that, they also have a great learning center with tons of resources.
Yeah, I'm actually participating in that. I have one of my courses on offer this fall, which I would love for people to take advantage of. The Acers Learning Center offers really in-depth, on-demand research courses. For example, they've got automated experimentation in materials synthesis and characterization. That's going to be awesome. You could expand your insight into topics like AI and ML. Of course, the course I'm teaching is tools for visualizing and understanding the structure of crystalline ceramics. So we're going to get into refelt refinement. We're going to talk about diffraction, understanding crystal structures with modern tools. Really, there's some great stuff here, and you get it for cheap, right? And you get it at a discount. If you go to ceramics.org/materialism, or if you use the code materialism, all caps, you will get $100 off your next on-demand course registration. So check it out. Don't sleep on it.
The Materialism podcast is also sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
And as always, we are so excited to have you guys a part of the show. I just got back from a conference where I met with so many listeners. It is absolutely unreal to be connecting with audience members from around the world. We would love, love, love to hear more feedback on what stuff you guys want to hear. You can find us at materialism.podcast@gmail.com or the @materialismpodcast on Instagram, or pretty much everywhere you want to find us. We are out there, and we love hearing feedback on the show. Special thanks to the people who make the music possible for this show, Alphabot and Kolobyte. We appreciate you. And that's it. We will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.